One of Spacetime's most requested topics is the controversial EM drive. They flooded in since Eagleworks Labs published a paper detailing their tests of an EM drive in a hard vacuum chamber. Those tests were consistent with a positive result, a real thrust. Today, we inaugurate the Spacetime Journal Club by taking a very careful look at this result. We've avoided the EM drive in the past because the results were inconclusive and the proposed physics was either very wrong or way too speculative. We walk a fine line as science communicators. Talking about hypey stuff is fun and popular, but it skews the public impression of what is credible and what is not. Sometimes bizarre new results do turn out to be real. Most often they turn out to be in error, like Opera's faster-than-light neutrinos and the Bicep 2 primordial gravitational waves. My guess is the EM drive results will end up with a similarly mundane explanation. But you guys have been asking for it, that's why I want to cover this as a discussion of the paper, what we call a journal club in academic circles. So, for edition 1 of the Spacetime Journal Club, we're jumping into Harold Sunny White et al. 2016, Measurement of Impulsive Thrust from a Closed Radio Frequency Cavity in Vacuum. First, a bit of background. The structure of the EM drive is a tapered copper cylinder with two flat ends. A resonant radiation field is induced inside, so microwave standing waves reflecting between the ends. The device was invented by Roger Scheuer in 1999, and a couple of similar proposals followed, most notably Guido Fetter's Canet drive. These fall under the family of microwave resonant cavity thrusters. They propose that thrust, a net force in one direction, the fat end for the EM drive, can be achieved by extracting momentum from the internal radiation field, but with no propellant. This would be pretty revolutionary because conventional rocket engines are fundamentally limited by the fact that they have to carry not just an energy source, but propellant, a bunch of mass to shoot out the back end to push them forward. The law of conservation of momentum demands this. Roger Scheuer explains the EM drive's alleged thrust as resulting from differential radiation pressure between the two ends. The best quip I've heard against this explanation is by Caltech's Jim Woodward, who pointed out that it's like trying to accelerate a car by getting in the driver's seat and pushing on the windshield, which is to say, this explanation breaks the law of conservation of momentum. Unless those photons actually escape the cavity, then any momentum exchange between the cavity and radiation field gets redistributed again because the system is closed. And if photons do escape, then you've just built a photon thruster. The thrust they produce is tiny, and much smaller than the thrust that Scheuer reported when he tested his own EM drive. The Eagleworks result is the latest in several attempts to reproduce Scheuer's measurement, none of which are close to being conclusive. Eagleworks itself had previously tested the device in air at atmospheric pressure and found a positive thrust. The main criticism of all non-vacuum tests is that thermal convection in the surrounding air may have produced the observed force. You're basically running a microwave oven, and so things heat up. But the latest test was in a vacuum chamber at 1/10 billionth of sea level atmospheric pressure, so no convection is possible. Thrust was tested with a torsion balance, basically a stiff metal wire on which the device is hung with a counterbalance. Twisting of the wire gives an extremely precise measurement of any force. It's the same tool that Henry Cavendish used to first measure the teensy tiny gravitational constant over 200 years ago. The Eagleworks test was performed at 3 power levels, 40, 60 and 80 watts. The authors claim a positive thrust in the expected direction at all power levels, and that direction reversed when device orientation was switched. The thrusts were reported to be the same as those observed in a non-vacuum. The average thrust to input power observed was around 1.2 millinewtons per kilowatt. That's vastly smaller than the thrusts observed by Scheuer's experiments, but still much larger than for a photon thruster. By the way, at 1 millinewton per kilowatt, It would take around a gigawatt of power to levitate a good-sized human, so the power output of a typical commercial nuclear power plant, or the power consumption of a time-travelling DeLorean. But eliminating the need for a propellant may mean that measly thrust-to-power ratio is useful for very long-range spaceflight. Definitely not powerful enough for hoverboards though. Sorry. So I have a gripe about the reporting of these thrusts. The author suggests a consistent thrust-to-power response and fit a straight line to the thrust versus power graph. However, it's really clear that the 60 and 80 watt powers are statistically equivalent and there's a huge scatter. That straight line is misleading. That said, the positive displacement still looks statistically significant. So does the EM drive generate thrust? Well, not until all other possible causes are ruled out. The big one seems to be that thermal effects could still be a factor. In particular, deformation of the device or the scale due to thermal expansion. A simple test would be to heat the device without a radiation field to see if that heating produces a similar false positive signal, but this hasn't been done yet. The authors identify several other potential sources of false positive signal and either make reasonable arguments against them or propose tests to rule them out. Before we can believe that the thrust is real, those tests need to be done. Any result that requires new exotic physics demands that all mundane causes be exhaustively eliminated beyond reasonable doubt. So the last part of the paper talks about a connection between the EM drive and pilot wave theory. This isn't something we can get into properly without first doing some quantum field theory, so I'll keep it brief. The paper invokes pilot wave theory as a way to justify treating the quantum vacuum as a sort of plasma with which it can exchange momentum. However, it's highly speculative and isn't necessarily even an obvious outcome of pilot wave theory. Our understanding of the quantum vacuum in standard quantum field theory doesn't allow you to push off it like you might row a boat on a lake. To exchange momentum with virtual particles over a distance longer than a Planck length, those particles need to become real. Photons would need to give up their energy, producing particle-antiparticle pairs. That is an understood process, and it does happen, but it's not what's happening here. If it were, those particles would also be trapped in the cavity, or if they escaped, they'd be a propellant and momentum would be exchanged with no more efficiency than a photon thruster. The authors don't claim this, by the way. Instead, they invoke pilot wave theory to justify treating the quantum vacuum as a deformable medium. In two separate papers, Harold White performs computer simulations which he argues demonstrates that such a medium can reproduce certain quantum observables like the energy levels of the hydrogen atom. If the quantum vacuum is some sort of almost classical medium, then they argue that the EM drive could push off it, leaving a wake of degraded vacuum behind it. However, none of this is relevant unless the founding assumption is right, that the vacuum is something very different than described by the otherwise amazingly successful quantum field theory. All of that said, if the observed effect really is a thrust, then something is causing it. The most likely explanation is that more careful experimentation will eliminate the apparent thrust. The second most likely explanation is that it'll be explainable with old physics. A distant third is that it's something brand new like this quantum vacuum stuff. Still, I look forward to Eagleworks and other teams getting to the bottom of it. Okay, that's my take on this paper. This is Spacetime Journal Club, which means it's now open for discussion. Feel free to pick apart my analysis in the comments. Back to our regularly scheduled, slightly less speculative science next week on Spacetime. Hey everyone. Before we get to the comment responses, I want to give a big thank you to Joel Brinton for his incredibly generous Patreon sponsorship at the Quasar level. Joel, we're considering buying a lightly used EM drive with your contribution. Only 1,000 light years on the clock, apparently. And thanks again to all our Patreon contributors and to you folk who are about to click on the link here or in the description. It really is a huge help. Okay, so in our recent episode, we talked about whether alien civilizations could possibly detect us from our radio transmissions. Let's get into it. Harlan Kempf asks whether a radio interferometer could be built across multiple planets, and what would be the effect on resolution. In principle, yes, as long as the timing between the antennae can be kept precise enough so that when you bring the data together it can be properly correlated. Then I can't think of any fundamental impediment. The resolution would be of a telescope the diameter of the antenna separation, so crazy good. In fact, the smallest angular size resolvable is proportional to 1 over the antenna separation. So if the 3,000 kilometer array can see an orange on the moon, an Earth-Mars interferometer could see that orange, well, crudely a structure 1,000 oranges across in the Alpha Centauri system. But I'm no radio astronomer, so there are probably enormous difficulties in actually achieving that. Still, sounds like a great idea. And yeah, extra dishes will both increase the field of view and improve sensitivity. Sun Power Guru argues that SETI is pointless because there's no good reason to think that aliens would use, for example, radio. Well, actually, there are good reasons to think that alien civilizations will use similar technologies to us. It's a fallacy to assume that technological development can happen via unpredictably divergent paths. Physics works the same everywhere, and there really are better and worse ways to do things. It's common to draw analogies between technological or intellectual gaps, like we are to aliens as ants are to us, or similar. But that's only useful to a point. Intellectual capacity may scale upwards indefinitely, but the availability of new types of physics to power new technologies has a limit. At some level, we start to have a pretty thorough grasp of what is possible in this universe, and the scope of new findings grows narrower and narrower. It's certainly possible that we're missing some amazing physical phenomenon that will make electromagnetic communication redundant. But honestly, it doesn't seem likely. There's very good reason to think that aliens will use light, whether radio or otherwise. Speaking of not using radio, Richy Rich and Gareth Dean had a nice discussion on whether aliens would use radio waves. Mr. Rich suggests that lasers, and even grazers, gamma-ray lasers, are much more efficient for targeted long-distance communication. I agree. There are even plans to use lasers to communicate between the hopefully upcoming Starshot LightSail mission to Alpha Centauri. But as Gareth Dean points out, lasers suck for broadcast, so sending a signal broadly. Radio is much better at that, and so is the natural choice for reaching many listeners, or if you don't know where your listener is. And Richy is correct in countering that an advanced civilization may not be so leaky with their own broadcast signals. Since the 1960s, our own radio leakiness has diminished with narrowing broadcast frequency bands, fiber optics, etc. It may be that an emerging civilization's radio loud bubble is really a very thin shell, and so catching it could be extremely lucky. Unless those civilizations are deliberately broadcasting to find us. In that case, radio is still the way to go, and it's worthwhile for us to search at radio frequencies. Musaya Kitsune is confident that we'll first make contact with an alien civilization by discovering some form of universal internet based on entanglements. Okay, I'm just showing this one because when I quit this gig to write science fiction books, I'll be stealing every single one of my ideas from old Spacetime comments. And now you can't accuse me of not giving credit. Oh, and I'm stealing Ryan's idea also. He suggests that the first message we get from aliens might be, "Stop broadcasting, you are in danger." Seriously, Ryan, you gave me nightmares.